Earlier lectures on quantum mechanics, we have arrived at time-dependent Schrodinger equation like this, where psi is the wave function, which is a function of r and t, which describes the wave packet related to a microscopic particle. As per Born interpretation, this gives you the position probability density, and the particle flux is measured by the probability current density, which is a function of position as well as momentum, because momentum enters in this through the gradient. So the uncertainty has some role to play in the accurate determination of probability current density. Then if the potential V is not time dependent, then we can decouple the space and time part by the separation of variable techniques, and this is the phi is that special part of the wave function which satisfies this equation, which is the time independent Schrodinger equation. This is time independent Schrodinger equation. Now look at this equation. This is a wave function. This is we may assume we may look it as an eigenvalue equation. This is the matrix. This is the column vector. This is the eigenvalue, and this is column vector. So for different eigenvalues, we will have different eigenvectors. That is the special part of the wave function phi. So we have designated the wave function by a subscript e, which reminds us that it is the eigenfunction of the Hamiltonian corresponding to the energy E. Let me cite few examples which we have done already. 1D free particle. 1D free particle, where the energy expression was E is equal to h line square k square by twice m. There were no restriction, and the particle wave function was given to be, apart from some constant, e to the power plus minus ikx. So we write it as k. So it is it represents the plane wave having momentum k, or wave vector k. The corresponding energy is this. Plus sign denotes a wave traveling towards the positive x direction, and minus sign a wave traveling along the negative x direction. Since there is no quantization, the wave function has been denoted by a continuum subscript. If we want to generalize it to 3D free particle, in 3D free particle, the energy expression will be E is equal to h line square by twice m kx square ky square kz square, and the wave function would be vector k plus minus r where plus sign again corresponds to a wave which is traveling along the direction of k, and minus sign denotes a wave which plane wave which travels in the direction of opposite to k. This is being Hermitian operator. The wave function called the eigenvalues are real. The wave function corresponding to the different eigenvalues are orthogonal. So the orthogonality condition, if we assume this, so the different eigenvalues means E and E prime, they are different by K and K prime, where E is related by this, E prime will be E prime, and this will be K prime. So the orthogonality condition here reads as this is delta function in 1D. This is delta function. The exact So if you want to put it equal to sign, then it will be normalized, and for 3D case the normalization condition would be integrated over V. This is a three-dimensional delta function. This much is about for continuous energy spectrum. Let me denote this or apply this to a situation where the energy value is quantized. 1D potential well, we have also solved the problem. So 1D potential problem, 1D infinite potential well. The wave function was found to be phi n of x where m is the mass of the particle, a is the width of the well, and in that case we have denoted this in terms of discrete suffix because the system is quantized. And the orthonormality condition reads as here we have different energy means different quantum numbers em star x en x dx from 0 to a, that is all space, is equal to delta mn. Its generalization to the 3 dimension is obvious. So what we have discussed right now is the orthogonality property of the wave function or of the orthogonality property of the wave function or the eigenfunctions of the Hamiltonian Hermitian operator. Hermitian operator has another very important property. Apart from the fact that its eigenvalues are real and eigenvectors corresponding to different eigenvalues for non-degenerate cases, orthogonal, the eigenvalues form a complete set. What does it mean? That means if we consider a function as, for example, in this case, any function in the range 0 to a, any function, well-behaved function in the 0 to a can be expanded by the by this wave function phi n, where n ranges from 1 to infinity. This is the meaning of completeness. If we count, so we write the completeness or the any state of a function as, this is not an eigen, not necessarily an eigenstate, summation over I is equal to 1 to infinity ci phi I of x, where phi I of x satisfies this condition. H operating on phi I of x gives you ei phi I of x. That is this equation, where ei is given by this. What does this mean? Let us consider an electron, hydrogenic electron. Then the hydrogenic electron can be in one state, its ground state, and the corresponding quantum numbers for an hydrogenic electron. This may be in one state. So in one state it has n, l, ml. For the time being I am omitting spin. So this is 1, 0, 0. It may be in two state. It may be in 2p state. 2p states have projection 0 and plus minus 1. So this is 2, 1, And similarly it may be n is equal to 3, so 3s 3p, only these two column will be the same, only here you have 3. Now come to the 3D state. 3D state, n is equal to 3, l is equal to 2, and here we have 0 plus minus 1 plus minus 2, so there are 5 sets. So this is 0 plus minus 1 plus minus 2. These are the projection quantum numbers. So let us consider a measurement which identifies this. Let me consider a thought experiment which can identify the state of the hydrogenic electron. One may, after experiment, one may get a combination that the electron was in this state. Someone else could also found the electron in 3D 0 state or any other state. Then the question arises, what was the state of the system before the measurement was made? Then one says that before the measurement is made, the system is in a superposition of state, where the superposition we have expanded the general state or the superposition state in terms of the eigenvalues of the Hamiltonian of the system, or eigenfunctions of the Hamiltonian of the system. So the state which represents the hydrogenic electron will be combination of all these states. So when the measurement is not done, it is in the superposition of state. Once the measurement is done and it is found that the system is in a state I is equal to 5, then from the superposition state it is being tracked to a I is equal to 5 state. Then it is no more in a superposition state. In this connection, Schrodinger's cat experiment is very interesting. A cat was supposed to kept in a box fitted with a door, and there was a probability that on opening the door one may get a dead cat or an alive cat. So the question arises, what is the state of the cat before the experiment was made? Here the experiment is opening of the door and looking at the cat. This is the experiment. So it is found that this state is dead cat, wave function of dead cat, plus alive cat, plus wave function of the alive cat. So it says that whenever no measurement is done, this is the superposition of state. The cat was in this state. If one finds that dead cat, for dead cat we have CD is equal to 1 and CA is equal to 0. For alive cat we have CD is equal to 0 and CA is equal to 1. These are after experiment. This is before experiment. Note the difference. Before the experiment was met, the system will be in in a state where all the possibilities have been included. So it is the superposition state, and once the measurement is done, the system is dragged to a specific state. There is no superposition specific thing. This is very important principle, superposition. Let me go with this superposition of state. This superposition principle of quantum mechanics is far more powerful than the superposition principle that we have used in wave mechanics. In waves and optics. So superposition principle. This is essential for the description of the system. So we write superposition of function is this: summation over I, sum over all state, Ci phi I of x. I am considering one dimensional case where generalization to 3 dimension is obvious. Where expansion is made in terms of the eigenfunction of the Hamiltonian. Two things yet to be described: how to find out the C expansion coefficients, and what is the physical meaning of it. The two things are left. To find out an expression for C, I multiply this term by phi star j x phi of x. This is the superposition of state, and this is one of the eigenstate, and expand it and integrate it over all space. On the right hand side, this is not will not enter into the integration. So this is psi I phi j star of x phi I of x dx. As if we assume the wave function to be normalized, then this is simply delta ij. So this is summation over Ci delta ij. This is equal to Cj. So which enables us to find out Cj is equal to phi j star of x, superposition of state. So if we want to find out the jth expansion coefficient, we must multiply the superposition state wave function by the conjugate of the wave function corresponding to the j and integrate over all space. We will get the expansion coefficient. What is the meaning of the expansion coefficient? The superposition state has to be normalized. That is, this has to be 1. So what should I write for this star? This is I write it as this is for phi star. So star is done, and this is first thing. We take the summations out. So I and j. This will come out to be as Cj star, and this will come as Ci, and this will be phi j star. Over all space. So again this is delta ij, so the result will be Cj star Ci delta ij. So one sum will go, and the result will be summation over let j, so Cj modulus square, and the result is equal to 1. So we may say that C1 square is C1 modulus square is the probability of finding the particle in the state phi 1. Similarly, C2 modulus square is the probability of finding the particle in the state phi 2. So that the sum of the probability is 1. So this is the, so we write C modulus square is equal to probability of finding the particle in pi I state when it is applied to the superpositions. Now the question that arises is what is the energy of the system. Thus, and then I'll first let me find how energy is calculated when the system is in an eigenstate. We do evaluation of energy. What we do, we have we multiply this by the corresponding quantity with star, and so this will be ei phi I star of x, and then we integrate the whole thing over dx, and this is due to the normalization condition. We will get ei. So the prescription of getting ei is simply this. If we want to find out energy of the I in a state, then we multiply and integrate over the space. This is the prescription. So if we want to find the energy of this energy corresponding to this state, so let energy E for the state phi of x is equal to summation over I Ci phi I of x. Firstly, we apply this by Hamiltonian. So this is the Hamiltonian operates on summation over I phi I of x. It will not operate on this, so the constant. So this is here we have replaced this by the eigenvalue equation. Now, to obviously this is not something into phi. So first thing, we can conclude that this is not an eigenfunction of time independent Schrodinger equation. This is not an eigenfunction of time independent Schrodinger equation. So we want to find out the energy of it. So E, we multiply it from the left. For this we use the j subscript. So the sum that will come out to be ij. So this is Cj star, Ci and Ei. These are not the integration variable, and the result is pi j star x pi I of x dx. This is delta ij. So this will be 1. So what is the energy of the superposition of state? In the superposition of state, the energy of the different eigenstate will come in the proportion in which they have built the state, the superposition of state. This is the probability of finding the particle in state 1 will have the weightage. So this is the probability of finding the particle in J state, and so the total energy is the weighted average of the state's energy. Now let me apply this concept to a simple problem. Consider a particle within an infinite potential well. So we know the wave function and we know its property. So the wave function is the particle 1D box. In 1D box we know the wave function I So we consider a general state as being this. The condition that must be satisfied by the wave function is that it should be 0 at x is equal to 0 and x is equal to a at the extremities. It indeed satisfies this condition. If we apply the normalization condition that phi star phi dx integrated from 0 to a is equal to 1, that immediately leads to a is equal to 30 by a to the power 5. This is a to the power 5. Now we expand this in terms of eigenstates. Where I runs from 1 to infinity. So to find out Ci, so Ci is equal to phi I star x, phi of x dx from 0 to a for the present case. So this is 2 by a, this coming from the normalization of this, and a from here, then the rest thing is x minus a sine I pi a x dx from 0 to a. We may evaluate this Fourier integral first and the result comes out to be 8 upon 15 by pi cube I cube. It is found that in this particular case C1 modulus square is 0.99. So that says that it is the 99% probability of finding the particle in the state 1. And in the state 1, the wave function is simply pi x by a. At first sight, it seems that these two are widely different. How can there be a probability of more than 99% of finding the particle in this state? This is because of the fact that the wave function, this wave function is a parabolic one. This is the superposition of state, and this phi 1 state is of this type. This is phi 1. And actual drawings would say that the mismatch is very small. Mismatch is very small, so the particle can aptly be represented by the single state only. In other cases, the problem one needs to consider a large number of states. Now, till now, what we have done, we have considered the time independent Schrodinger equation and argued that the wave functions or the eigenfunctions of the Hamiltonian forms a complete set of orthonormal bases. So any function in this and the space can be represented in a as a linear combination of this eigenfunction. And we also have shown that the superposition of state for which is obtained from time independent equation is not an eigenfunction of the time independent Schrodinger equation. Now let us go to the time dependent case and apply, see what happens. Superposition in time dependent case. In time dependent Schrodinger equation. The time dependent Schrodinger equation is and we denote this wave function again by a subscript e because we know that when the system is found to be quantized or have been discrete spectrum, then the sum will be over the continuous discrete spectrum. Let us apply the superposition of state. The superposition of state is this. Note that this is an eigenfunction of the solution of time dependent Schrodinger equation, and we have made a superposition of these states. So writing explicitly, this is now from the solution of time dependent equation we get the different equations, different eigenvalues and different eigenfunctions, corresponding eigenfunctions. We expand the state in this way. If we include all the state, it is the representation of the wave packet. This represents the wave packet. Let me first check whether this is an whether this equation satisfies this equation. So to this end, I write I h cross del psi del t. This is equal to I h cross del t operating on the superposition of state when this operates this is Ci, and what we get back is minus I ei upon h cross times Ci phi I of x e to the power minus I ei t upon h cross. So if we take this out, this h cross goes, this is plus, no factor is there, or summation over I. And the whole thing is phi I of xt. This part we can assume to be like this. When H operates on this, gives you EI times this. So what we see? We see that this is an eigenfunction of, or satisfies, this equation satisfies time dependent Schrodinger equation. Note that for the time independent case the situation was different. Now what is the probability density in this state? The position probability density. Probability density, if we consider the system in such a superposition of state, the probability density of finding the particle in x and t is equal to psi star xt, psi of xt. For psi star we use j subscript, and for psi I subscript. So the result will be ij. This is Cj star Ci phi j star xt phi of xt. If we write it in terms of the if we write it in this form, then this becomes e to the power t by h cross. Here we find that the probability density depends on time, so such a state is called non-stationary state. Rho of xt depends on time, so psi is as obtained as the combination of Ci psi of xt is non-stationary state. Non-stationary state means probability density is a function of time. On the other hand, if we could consider the time dependent equation for a particular eigenvalue, then the probability for compare this with this. In that case, the situation will be phi I star of x, phi I of x, and there is no time dependence. This is stationary state. So we define stationary state as one for which the probability density is not a function of time, and for if the probability density depends on time, the state is said to be non-stationary. And we have found that in general this state if we expand the wave function in terms of the solution of time dependent Schrodinger equation, we generally leads to a non-stationary state. But if we integrate this and apply the continuity condition, so if we integrate this, what we get? If we integrate this is basically rho of xt, so we will lead to this summation over ij cj star ci. Then this part will not be within the x integration, so it is e to the power ej minus ei t upon h cross, and the integration is over phi j star x phi I of x dx of over whole space. This is delta ij. When delta ij this becomes 0, and the result is summation over ij cj star ci delta ij is equal to summation over I or j, whatever you like, cj modulo square. So same, the expansion coefficient can be assigned the same there is the same significance as we did in the case of time independent Schrodinger equation.